So what can we do if the model is unknown? In high-dimensional settings, like in the game of Go, it seems hopeless to learn explicitly the reward structure and the transition structure. There are just too many states and actions that can be taken, and too many states and, that can lead to an end of the game. Now, instead of learning explicitly the reward and the transition structure, what MuZero demonstrates is that it is possible to use Monte Carlo tree search with a learned latent representation of observations and a learned dynamics model. In spirit, this is similar to the model of variational state tabulation that I presented to you earlier, where latent discrete representations were learned from the raw observations of videos in the Doom environment. And the dynamics model there was just a tabular model that mapped these discrete latent states. In MuZero, you will learn that these latent representations are not discrete, but they're actually vectors. And it is because of Monte Carlo tree search that it is possible to operate with these vector-valued latent representations. The value iteration, so this background planning, would not be able to efficiently deal with these vector-valued latent representations. The publication of MuZero actually shows that with this approach it is possible to reach state-of-the-art performance not only on board games, chess, shogi, and Go, but also in the domain of Atari video games. The model of MuZero consists of three connected components for representation, dynamics, and prediction. The initial hidden state S0 here is obtained by passing the past observation or the current observation here, for example the Go board or an Atari screen, into a representation function H. Now this is really now where Monte Carlo tree search can start. Now given a previous hidden state sk-1 and the candidate action ak, the dynamics function g here produces an immediate reward for this action and state and a new hidden state sk. From this state sk, the prior policy p and the value function v are computed by the prediction function f. So this part you know already from AlphaZero. That's really the part that we have seen there in the selection process and then in the backpropagation process where the values are backpropagated. What is new in MuZero is that the representation function h and in particular also this dynamics function g are learned. Note here that the dynamics function g in this case is deterministic, so it learns a deterministic transition and not a stochastic transition. How is MuZero then acting in the environment? It is basically exactly in the same way as AlphaZero is acting. So a Monte Carlo tree search is performed at each time step t, as described on the previous slide, and represented here with this little graph. The output of this Monte Carlo tree search is this policy pi t that we have seen in the part on AlphaZero, which consists basically of the counts for the different actions that can be taken in the leaf node. And from this policy, actual action is sampled, which is proportional, as I said, to the visit counts for each action from the root node. This action is then performed and a new state is generated. So yeah, the environment receives this action and generates a new observation OT and an actual reward UT plus 1. And this continues now for multiple steps until the end of the episode where the trajectory data is stored in a replay buffer. Actually, it's really just this replay buffer in this case is really just to train afterwards the functions g, h, and f. So this is how these functions are trained. A trajectory is sampled from the replay buffer, and for the initial step, the representation function h receives as input the past observations O1 to OT from the selected trajectory. Now, the model is now unrolled recurrently for k steps, so it's like running again the dynamics that is used also in the Monte Carlo tree search, but it is using the dynamics function g and receives as input always the state sk-1 from the previous step and the real action that was actually taken in this episode. So this is coming all from the replay buffer. Then the parameters of the representation, the dynamics and the prediction function are trained jointly, end-to-end, just by backpropagation through time, to predict the three quantities: the policy, pk, which is used to do focused selection in Monte Carlo tree search. Again, this is the same training loss as we have seen in AlphaZero with the cross entropy, that the policy here should match as close as possible the policy of the actual Monte Carlo tree search. Similarly, the value function should match as good as possible the future discounted reward in this case, and the immediate reward is learned as well for the different states, which is important, for example, in the Atari video game setting, where this set t plus k is really the sample return, either the final reward of the board games or the end step return in Atari, as I said before. So by just using this encoding to latent representations and this dynamics function and combining it with the parts that were already present in AlphaZero, it is not necessary anymore to hard code to really give to the Monte Carlo tree search the rules of the game. And now with this model, with this learned model, MuZero can be applied not only to chess, shogi, and Go, but really also to all the Atari video games. And you can see here that it reaches or even becomes better than state of the art until now. So this is AlphaZero here, state of the art, and this is, I think, R2D2, a specific model-free reinforcement learning method that was until now state of the art on Atari video games. The solid lines, I think, are the mean, and the dashed lines are probably the medians. And you see that in both measures, the blue curve, which is for MuZero, surpasses at some point the previous state of the art. So instead of relying on a given reward and transition model, MuZero learns an encoding of observations to states with this function h, and a transition function from states to next states with this g function. Like AlphaZero, it relies on Monte Carlo tree search with a learned function f that estimates the action probability p to be used in the selection step of Monte Carlo tree search, and the value v for the states to be used in the backup step of Monte Carlo tree search. Let us conclude the third part of this lecture with a quiz. With background planning, decision making is computationally very cheap, since we can just use the Q values to find the optimal actions at decision time. Is this correct or not? This is correct. With value iteration, we can find the Q values, and at decision time we can just use them to find the optimal action. In Monte Carlo tree search, decision making is computationally very cheap, since one can use the Q values to find the optimal action. Is this correct or not? This is not correct. In Monte Carlo tree search, At decision making, we expand the whole decision tree. It is a method of planning at decision time planning. And we cannot just use the Q values to find the optimal actions, but one can use the Q values to find in the selection part of Monte Carlo tree search, but not to find the optimal final action. In AlphaZero's Monte Carlo tree search, the actual actions are sampled from the prior action probability PSA. Is this correct or not? This is not correct. In fact, this prior action probability also helps in the selection process to search in promising directions and rule out parts of the search tree that are not useful or not promising. In AlphaZero's Monte Carlo tree search, the prior action probability is trained to be as close as possible to the actual policy of Monte Carlo tree search. Is this correct or not? This is correct. The prior action probability should actually be as close as possible to the actual policy of Monte Carlo tree search, since this would help to focus on actions that are relevant in the selection step of the Monte Carlo tree search. However, the prior action probability will almost never be as good as the actual policy of Monte Carlo tree search, unless we have infinite training time almost. The latent representation of AlphaZero is a binary word, for example, 10110. Is this correct or not? This is not correct. The binary word was used in variational state tabulation, but in AlphaZero actually real valued vectors are used as latent representations. And these real valued vectors in the latent representation of AlphaZero don't have any meaning really, but they're just used to predict future actions and rewards and values as good as possible. With this now, we come to the end of this lecture. You have seen in the first part that the problem of correlated samples can be solved with a replay buffer for off-policy model-free reinforcement learning, for example DQN, or multiple parallel actors for on-policy model-free reinforcement learning, for example A2C. In the second part, you have seen that both on- and off-policy deep reinforcement learning methods can be adapted to continuous action spaces by either making policy gradient methods more sample efficient and robust, think of proximal policy optimization, or adding a deterministic policy network as, for example, in this deep deterministic policy gradient method. Now in the last part, you have seen that in model-based reinforcement learning, we can use background planning, for example value iteration, in moderately sized state spaces, and decision time planning, like Monte Carlo tree search, for large state spaces, and rely crucially really here on learned state abstractions to perform planning not on the level of raw observations, be it board games or observations in the Doom environment, but rely on compressed and learned representations. Thank you for your attention and goodbye.